All right, hey guys, we're back. This is video number 2. All right, so video number 2. So we're picking back up with the same exact equation we've been spending a lot of time talking about, and here is the K expression for it, concentration of products, which is only 1, raised to its coefficient, divided by the concentration of the reactant. What I wanted you to see is I wanted you to see what I said before, which is that the only thing that can change the equilibrium is the temperature. It doesn't matter what you start with initially. Now, I can tell you it doesn't matter what you start with initially, but it doesn't mean anything until you actually sort of see it. So here, these are 4 separate experiments. So in experiment 1, they started with no reactant and only product. Okay? They achieved their equilibrium concentrations, and the K expression was 0.211. So then what they did was they ran a second experiment where again they started with no reactant and a little bit more product this time. So look at their equilibrium concentrations. So the equilibrium concentration of the reactant went up and the equilibrium concentration of the product went up. But what didn't change? K. Because it is an expression, because it relates the two to one another. Because they're either both going to go up or they're both going to go down if you change the initial concentrations. So K, then, the relationship of the two isn't going to change. All right? Again, look at experiments 3 and 4, completely separate initial concentrations. Now, in this case, they actually do have the same equilibrium concentrations, which is possible, right? But again, look at all 4 of these K values. Yeah, they differ by 2,000th of a decimal place, which we consider to be irrelevant. Okay? But how are they getting this K? Well, they're essentially just plugging in some numbers. So let's take the first numbers from the first experiment. So here is my concentration of NO2 at equilibrium, right? You do not put initial concentrations in K. K is literally called the equilibrium constant expression, or this entire thing, Kc and the fraction. Where's my mouse? I can't find it. Oh yeah. Kc and the fraction, this is the equilibrium constant expression. And then Kc is called the equilibrium constant. And you do not put initial in because literally it has the word equilibrium. So here's my equilibrium concentration of NO2 squared divided by my equilibrium concentration of my reactant. Or let's take the second one. Equilibrium concentration of the product squared divided by the equilibrium concentration of the. It doesn't matter which experiment you choose, you're getting the same thing. Okay? You're getting the same thing. All right. So now let's look at this in a plot. Okay, so we looked at it as data points. Now let's look at it as a plot. So here we have time on our x-axis, and we have change in concentration of NO2 as my y-axis. Take a look at experiment 3. So we started with only products, so its concentration went down until it hit the equilibrium and then it didn't change. In experiment 4, we started with only reactants, so we didn't have any NO2, so its concentration went up until it hit this equilibrium point at which it no longer changed. Now, how these two are equivalent, that has to do with the actual numbers here and the fact that NO2 is squared. But don't worry that you can predict. I'm not going to ask you if you can predict if 2 reactions would have the exact same equilibrium constant expressions. I'm just showing you that, again, the reason why K is the same here is because they're reaching the same equilibrium because we didn't change temperature. The only thing, so this is at 100 degrees Celsius, the only thing that's going to change the value of capital K is a change in temperature. All right, so again, let's keep driving this home, right? Here's some other plots. So in this plot, we're looking at the production of ammonia from nitrogen and hydrogen. And in this case, we started with hydrogen and nitrogen. So concentration of reactant went down, hydrogen. Concentration of the nitrogen reactant went down. The concentration of the ammonia product went up until we reached equilibrium. And then all 3 concentrations, which are completely different from one another, no longer changed, right? Or what if we had started with product and no reactant? So in this case, we're making hydrogen and we're making nitrogen and we're consuming ammonia to do that. But again, once equilibrium's achieved, take a look. Exactly the same. Okay? It doesn't matter what you start with initially. The initial concentrations do not affect the equilibrium. What affects the equilibrium is temperature. Okay? Where the equilibrium is going to lie. All right. Now, remember that I talked to you, though, that pretty much very rarely do we have an expression where the concentration of the reactants and products are exactly the same. I mean, consider every example I've shown you so far. I've yet to show you one because it just doesn't really happen, right? It's going to be that there are more products or more reactants. That's how these things work. So let's look at an example here. So we have hydrogen reacting with bromine to generate 2 HBr molecules. Now this is a snapshot at equilibrium, okay? What do you notice you see more of? You see a lot more HBr molecules, which means at equilibrium, this is definitely product favored. So how does that relate to the value of K? Well, concentration of product raised to its coefficient divided by the concentration of the reactants. If K is going to be a large number, think about your fractions. The numerator has to be big and the denominator would be small, okay? Which is exactly what we're talking about here. Lots of products, not a lot of reactants, K is going to be big. So what this means is if you know K, you know if the reaction favors the products or the reactants, or it doesn't favor either, right? Because if these concentrations were the same, then K would be 1, right? So if capital K equals 1, it doesn't favor products or reactants. If capital K is really big, then it favors the products. What's the only other scenario? If capital K is really small, right? So in this case, we're taking N2 and O2 and we're reacting them together to make NO. And if you look at our snapshot at equilibrium, you notice it is mostly reactant molecules, not a lot of products here. So again, what is this telling me? This is telling me that the reaction is reactant favored because at equilibrium, I have mostly reactants. And if the product concentration is the smaller number and your reactant concentrations are the larger numbers, and you're taking a small number and dividing it by a big number, that's going to give you a small number, right? So a reactant favored equilibrium is going to have a very small value of K. All right, so let's take a look at this example. So it says the reaction of N2 and O2 to form nitrogen monoxide might be considered a means of fixing nitrogen. And you have the reaction there. It says the value for the equilibrium constant for this reaction at 25 degrees Celsius is Kc equals 1 times 10 to the negative 30th. Well, the first question you have to ask yourself is this: is that a big number or a small number? And hopefully you recognize that that negative 30 means that this is an itty bitty number, right? Very, very small, which means what? It is reactant favored. So now, describe the feasibility of fixing nitrogen by forming NO at 25 degrees Celsius. When we put this in sort of simpler terms, is this reaction good at making NO? No, right? It's reactant favored. K was really small, which means we're not going to make very much NO at all. So if that's your goal, you need to pick a new reaction. NO is not going to work for you. All right? But there are times in which we want to know the K for a reaction and we don't know it. So we have to consider what are ways where I can determine a K if I can't go in the lab and actually study the reaction. because maybe it's super expensive, or maybe it is dangerous or something like that. Remember how we had the same issue with delta H in chapter 9? And we had this thing called Hess's law that allowed us to manipulate reactions and then add them together to come up with the delta H of the new one. We're going to do the exact same thing here with K's. But let me be very, very clear. None of the rules that you learned for delta H work here. And why is because delta H was a singular number, a singular idea. K is a fraction. Okay, and because K is a fraction, it means none of the rules that you learned for delta H are going to work. All right, now let's look. So here we have A plus B goes to give me C plus D. It's an equilibrium. C and D divided by A and B. That's my K expression. Well, what if I flip that? If I flip it, now I have C and D going to make A and B. So I would have the concentrations A and B divided by C and D. Now, when you flipped a reaction in chapter 9, what you did was you just changed the sign, right? You took a positive number and made it negative, or you took a negative number and made it positive. But that's not going to work here because what you've done is you've flipped a fraction. So taking the negative doesn't account for this. You have to take the inverse, okay? Because if I take the inverse of this, K forward, I will get K reverse, okay? All right, so do not multiply by -1. That does not handle the fact that this is a fraction. This is a fraction that you have flipped, which means you must flip it back. How do we flip it back? We take the inverse. All right. What about if we need to multiply by some coefficient, right? You did that when we talked about Hess's law, where, you may have needed to multiply an equation by 2, and you multiplied everything by 2, including the delta H. But that's not going to work here because the coefficients have a squared sort of, not necessarily squared, depends upon the coefficient, but they have an exponential effect on the concentration. So if you multiply by that number, that doesn't fix it, right? So here we have a sample expression and its corresponding K. Now let's say we're going to multiply each coefficient by some new value. So this N is some new values. So now your coefficient is N times C, right? Or N times A, or N times B, right? That's how it's going to work in this expression. Well, what do you notice? Since they're all raised to N, and we know N is the same, you could just pull N out. So that means you could just take this original K expression and raise it to whatever this new N value is. Okay? So again, if you multiply your reaction by 2, multiplying K by 2 is not going to fix this. That's what you did in chapter 9. That doesn't work here. If you multiply by 2, you need to square the K. If you divide it by 2, you need to raise K to a half, which is the same thing as taking the square root. All right? And then what's the last thing? The last thing is you need to be able to add K's together to come up with your new K, right? Because you're manipulating and adding equations together. Now, again, with delta H, you added the equations and then you added the delta H's. But that doesn't work here because this is a fraction. You're not going to add the K's. You're going to multiply the K's. Because when you multiply the K's, things cancel properly and you get what you need to get. Okay? So don't add K's, multiply them. All right, so we've hit our time constraint again. The next video is going to be me with a phone working through some examples of these, all right? See you in video 3.